Alright, welcome to short task number 2. What we'll be doing in short task number 2 is using this spreadsheet here, this oh, this facility here, and the instructions on Moodle to calculate the amount of pressure that a pump needs to overcome to move liquid in a couple of different ways in this facility. So this is nominally declared to be a winery, but it could be any facility whatsoever. And these same calculations would be used for calculating how much pressure needs to be overcome by a pump to move liquid from a dam to a sprinkler, or between two dams, or to shuttle it around an aquaculture facility, or any type of fluid really. So it's highly universal and highly useful. So we work out the amount of pressure that needs to be overcome. The total amount of pressure we calculate in meters of head, so essentially how far vertically does the pump need to pump the liquid effectively, and that's broken into the dynamic head and the static head. The static head, quite literally, is the difference in the height of the liquid in the supply compared to the height of the liquid in the discharge. And that allows us to work out how much gravity it needs to be overcome. So it's literally the vertical distance that the liquid needs to, or the pump needs to overcome to move that liquid. So if the liquid's 2 meters in the supply tank and 4 meters in the discharge tank, the static head would be 2 meters. In the assignment, we asked to do a fixed line method and a flexible line method, and we'll be looking at those actually when we look at the facility itself, because that has some ramifications on what the maximum head, or the contribution of the static head, is to that maximum head. But we'll discuss that when we look at the facility itself. The dynamic head, which is the other component of the total head, or total amount of pressure that the pump needs to overcome, is due to friction in the lines that the liquid actually moves in. So that's just like resistance in a wire. So let's have a look at the assessment itself. Move to the assessments window, and we go to short task 2, pump modeling. And this starts off by saying we've got our facility, which we've developed in short task 1, 4 fermentation tanks on one end of the winery and 2 on the other end of the winery. We want to move liquid from one to the other. It doesn't actually say how much liquid is in each, so we just have to assume, based on the information we're provided, what's needed. So let's have a look at that. First of all, it says describe the equipment required for each transfer option. So what are the 2 transfer options? The first one's a fixed line. So a fixed line is a line, a hose or pipe in a facility that doesn't move. It's actually fixed in place. And in this case, the fixed line goes from a tank over to the sidewall, up the sidewall, along the wall, and then discharges the liquid into the top of those large tanks. The flexible line option takes the liquid with a rubber hose from the outlet at the bottom of the supply tank to the pump along the ground, and then along the ground to the inlet of the discharge tank, which is at the bottom of the discharge tank. So what equipment's required there? Well, I've pretty much listed it out. Don't forget the pump, but we also need to work out the fittings. So we'll talk about the fittings when we have a look at the fixed line option on the production facility itself. So we need to work out the minimum and maximum total head for both options. What's the power rating of the pump required? Well, our spreadsheet will give us that. And then how many volt amperes is actually required by this winery. So that's talking about how, remember, some of the energy when we're running a motor actually is required to create the magnetic field around that motor. So the power station has to provide that to us, but we don't actually use it. So they charge us for that, and that's our demand, part of our demand charges. So we'll calculate that too based on a made-up power factor for our pump. And then I ask you to actually find a pump that would do that transfer for you. So let's go to the facility itself. Here it is. Now, I've just moved one tank here for the sake of the exercise so we can discuss it in a minute, but normally that wouldn't be there. I'll move it in a moment, and you can torturously watch me use Google SketchUp. So with the fixed line option, what we're doing is I've just put a little outlet on this tank here. So for the sake of the exercise, I want you to calculate the largest or longest transfer for each option. So with the fixed line option, it would be from this tank with, let's say, a stainless steel pipe over to the wall, up the wall, along the wall, and then out, essentially fixed to the roof, and then discharging down into that tank from the top. The flexible line option would be along the ground with a rubber hose to a pump, and then over to the base of our tank. So if we look at the fixed line option, the static head, that vertical distance, isn't going to change in any way due to the height of the liquid in the tank, because we're discharging liquid into the top of the tank. So it doesn't matter if that tank's empty or full, the liquid still has to get all the way above it. So the maximum static head for the fixed line option would be when the liquid is at the lowest point in one of these tanks at the bottom, and then is being sent over the top. So how high are these tanks? These tanks are 4 meters. So the total head would be around 4 meters, because we're taking it from the base of this tank up above this tank and then dropping it in. So the static head, the maximum static head for this transfer really won't change. What's the minimum static head for this transfer? Well, it'll be when the liquid is at its highest in the supply tanks. And that's because if we're moving the liquid from the base of these tanks over to the side wall, if that wine is, or if the liquid in that tank is right at the top, then we actually get 2 meters of head for free, because that liquid will move via gravity along this pipe and then up to the liquid level in the original tank. So if it's at 2 meters, we'll get about 2 meters of static head for free. So in that case, the static head for the overall system that the pump needs to overcome is just 2 meters. It's just the difference in height of the liquid level in the supply tank and where it's going, which is at 4 meters. So the minimum static head would be 2 meters, the difference between here and here. On the other hand, when we're doing a flexible line option, the static head is the difference in height of the liquid in our supply tank and the liquid in our discharge tank, because the liquid will be entering from the base. So at the start, our static head will actually be negative, because this tank here will be empty, this one will be full. So this one's actually 2 meters above where that liquid's going. So we actually get 2 meters of pressure for free. So that's actually a negative static head. So the minimum static head in the flexible line option is actually negative 2 meters. But as we transfer it, the height of liquid in the discharge tank actually begins to increase. This one decreases, so our static head will increase, the difference between the height of the liquid in the supply tank and the height of the liquid in the discharge tank. The maximum will be when we're finally filling up this discharge tank after pumping 2 supply tanks worth in there. So after we pump 1 tank in, it'll be half full, because they're the same diameter, and the supply tanks are half the height. And then we start pumping the second tank in, begins filling up here, and this one going down here. So the maximum static head will be when this one's empty and this one's full, and that's 4 meters difference. So again, the static head will be 4 meters. So no matter what we do in this transfer, the maximum static head will be 4 meters. The spreadsheet that I've provided you allows you to calculate the static head depending on the liquid level in the 2 tanks you're going to. So that, not in an ideal situation here where we know the maximum static head. So it's useful for that, but really for this exercise we know what the maximum static head will be. For both transfers it'll be 4 meters. So when we're doing the fixed line and the flexible line, we need to know the length of hose required. So we're going to come back here after we look at the spreadsheet and actually estimate the amount of hose required. So let's go to the spreadsheet and see how we can use this to calculate our overall pressure that needs to be overcome by the pump. Here we are here. So the spreadsheet breaks it into calculations of the static head. So again, we already know what the maximum static head will be, but we'll go through the calculations. The dynamic head, which is due to the friction, that's quite a lengthy calculation. All the maths is in the topic 3 notes. So we calculate that due. Dynamic head, the friction is varies depending on the velocity of the liquid due to turbulence. So we actually calculate the velocity of the liquid first. Then we calculate how much loss of kinetic energy is due to the fittings and the type of hose we're using. What's awesome about doing these calculations is it actually converts the friction from different fittings and it converts that into effective increase in length of hose. So we actually see how much, by using particular fittings, what the equivalent extra length of hose that is, which is kind of awesome calculation. And then it sums all that up and gives us a maximum and minimum total head. Here I've got some calculations that I did when I stuffed up the video before, which I think I'm in the process of doing again now. I'm not sure if I edited those numbers or not, but I've got rid of them. And then it calculates total head. So let's go through this. Let's do a pretend static head calculation. So it asks for the initial height. The yellow boxes are where we should add parameters in. The ones that aren't filled in will do automatic calculations. So the initial height of wine in the supply tank. So let's say we're working out the maximum static head. Initial height of wine in supply tank, let's say it's 2 meters because they're 2 meters tall. Diameter of the supply tank, they're 2 meters. So it's calculated the volume of the supply tank straight away. We need to know that just in case, well, what it actually uses is it calculates with when we know the diameter of the discharge tank, it'll actually tell us how high that volume of liquid will go in the discharge tank. And we need to know that to work out static head. Height of the bottom inlet in discharge tank above the outlet of supply tank. So that's asking, does the pump actually just need to lift the liquid a little bit even to get into the outlet of the discharge tank? So pretty much, is the discharge tank higher than the supply tank? In this case, no, it's not, so we put 0 meters in there. Starting height of wine in the discharge tank, let's say it's 2 meters, so we've already pumped one tank in. So it says here now, the maximum height of wine in discharge tank currently is 2 meters. Oh, sorry, that was diameter of discharge tank, 2. So pumping that amount of liquid into that tank with diameter of 2 meters will lift it 2 meters. That makes sense because the only difference between the discharge tank and the supply tank is the height. So maximum static head is 2 meters, minimum static head is -2. We know that because it'll just gravity into the bottom. Starting height of wine in discharge tank, let's say it starts at 2 meters, so this is our second pump in, and boom, maximum static head now is 4 meters. So it's actually calculated that for us, which is lovely. What if we put a 4 in there? That won't work. All right, so maximum static head is 4 meters, minimum static head is -2. So we get that little bit of gravity. All right, so we've done our maximum minimum static head. That minimum static head, of course, is when the discharge tank is empty. So let's go here, dynamic head. So let's now calculate so total head is the static head plus the dynamic head. We've got our static head. The dynamic head is due to friction in the lines. So it asks us what flow rate. So here we get to make it up. So we get to go, how much flow rate do we want? Well, we don't want to be standing around forever with our transfers. So let's say we're doing 10 cubic meters an hour, which is 10,000 litres an hour. It calculates that for us. Flow rate, that makes it 167 litres per minute, or 0.003 cubic metres per second. This, for dynamic head, we need the velocity. And velocity is speed, which is distance over time. Flow rate is volume over time. So what this does is converts volume over time to distance over time. And to do that, we need our flow rate and we need the diameter of our hoses. So in this case, I'm going to say we've got 5 centimetre diameter hoses. It asks us what the diameter of the hose in the suction hose is and the discharge hose, because sometimes you use mismatch hoses in some wineries where you can't find, say, two 2-inch hoses or whatever system it is. So it asks you just to put the diameter of the hose on either end in there, and it just does a straight average. Now the hose length might be different in the discharge and the suction end. So you can actually do your own weighted average there if you like, but I've just done an easy one where it averages the two. And then it gives the cross-sectional area of the hose, converts the diameter into cross-sectional area, just pi r squared, so it divides the diameter by 2, squares it, and multiplies by pi, and then it calculates the velocity. So that's movement of the liquid in meters per second. All right, so we've got that requirement, and again, that's all talked about in the topic 2 notes. Then it asks us, do we actually have any contractions of the hose? So sometimes you jam 2 different types of hose together and they might be different diameter. That actually changes the flow and adds resistance on movement. So it asks you, is there any cases where you go from a 2-inch to a 1-inch, 3-inch to 1-inch, or 3-inch to 2-inch? You can either put no or yes. If I put a yes in there, it actually says that adds effectively 1.5 meters of extra hose length to this transfer in terms of resistance. But we don't have that. Let's just say we have no contractions. Then it asks for fittings. Let's calculate this for the fixed line. I'll go back to the map. What sort of fittings do we need? Well, first of all, we need to send the wine in that direction, so we need a right angle there, so that's 1. Then we need the wine or the liquid to go up here, so we need right angle 2. Then the liquid's got to turn that way, right angle bend 3. Comes over here, right angle again, so right angle bend 4. And then it needs to drop down into there, right angle 5. So we've got 5 right angle elbows. So if we go in here, we can actually select the type of elbow. You have elbow with a long radius. So it's quite important actually is how long the bend is compared to the diameter of the pipe. It actually changes the flow within a plumbing system. So a short radius actually adds more resistance. So if we put a short radius there, it makes a loss coefficient of 30. That gets converted into meters of extra hose. Or here it is. That adds 1.7 meters of extra hose. If we put a long radius one in, it only adds 1.2. So fitting actually plays a really important role. What if we've got a 45? See, 45 degree angle, a bit less. What if we put a sharp corner on? Oh yeah. So a square corner, we don't have a nice rounded corner. That adds a lot of extra meters onto our transfer. What if we do a full 180 degree? Adds 4 meters. What if we put we've only got a T intersection and we make it go through the branch of the T intersection? That adds 3.2 meters. So that's not ideal. So fittings play an important role. Let's say we use the best one, an elbow long radius. We'll put those in each. Let's do 3 of those, and we'll say we ran out of those. We add a short radius one, and then we did a T intersection, and it has to go around the T intersection. Through the branch in the T intersection. All right, so using these fittings, we've added 7.7 meters of hose effectively. And then it says at the end you put in a butterfly valve. Well, butterfly valves or any valve only adds friction if they're partly closed. And have a look at this. If we start a transfer, and I think we've all done this, with the fitting partly closed, let's say it's half closed, adds 36 meters to the transfer. Let's say it's almost fully closed. Adds over 1 kilometer of effective hose distance. So let's say we've just had it 10% closed. So it doesn't make a huge difference. All right. So just using these fittings, we've added 7.9 meters of effective hose length before we've even actually calculated the length of the hose or pipe we're going to use. So let's calculate that now. Now this could be torturous again. I'm going to use the tape measure. I'm just going to roughly do this. So I'm going to go from this fitting over to the wall. It's 11 meters. I'm going to tap these into the spreadsheet at the same time. I have no memory. 11 meters. So we've got it go over the wall. Let's go up the wall. Let's go 4.17 meters. Let's go say 4.2. And we'll cut across. Golly, I hope that's the right spot. 22 meters. Can't believe I just used the word golly as well. Then we move over here. Oh yeah, I did go too far. So we'll take a meter off there, and then we'll. You can change the tape measure, but for expeditious reasons, I just won't do that. So let's just say it's 11 meters over to that tank. So 11 there. We'll take a meter off there. So the overall fixed line length is 47 meters. So over here, we put in 47 meters. And then it asks, what's the roughness factor? So different hose types add more friction depending on the type of material. And I've just put this in a table over here. Stainless steel, it's got a friction coefficient of blah, 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 blah. Plastic hose is the same. Rubber hose is, what's that? 25 times more rough. Adds 25 times more friction than the stainless steel. So here we just manually enter our friction coefficient. So I'll just copy and I'll paste that in. So our total dynamic head, so our hose length 47 meters. Our extra hose length due to the fittings is about 8 meters, so it's about 55 meters of extra hose. And then in the calculations, as specified in topic 3, see how that's bunged into an equation, and that gives us the overall meters of head that these fittings and hose have added, and it's 2.6 meters. So the pump actually has to overcome an extra 2.6 meters due to the hose length and the fittings. And then it adds our head together. So we've got the total head was 4 meters. It's added our dynamic head, giving us our total head. So our pump has to overcome 6.6 meters of total head. And look at this, our minimum total head is actually positive. Even though our minimum total head, we get that gravity bonus of -2. With all our fittings, actually, we don't have a negative total head anymore. So the pump has to actually overcome 0.62 meters for any type of transfer here, which is interesting, isn't it? That the all these fittings actually counteracts the effectiveness of gravity. All right, so we've got our maximum and minimum total head. So what we're really interested in with our pump is the maximum head. We need a pump that will overcome that maximum total head. So to work out the pump power rating, we need to put in a pump efficiency, and all pumps come with a rated efficiency. So that's how much of the energy that's supplied to them is converted into kinetic energy in the liquid. So let's say with a modern pump it's 90%. So here it's calculated, we only need a pump with a rating of 195 watts to be able to do this transfer. So a 195 watt pump will overcome 6.62 meters of head. Now importantly, it won't do it at 10,000 litres an hour. All that pump will do is overcome that head. So in a lot of energy efficient wineries, they actually use quite low powered pumps running for quite a long time. So they do really long transfers, and then they can run the pump off solar power or something like that. So you'd only need a 200 watt pump to do this transfer, but it'll take a long time. Importantly though is we have the maximum head, and when we go and look at pumps from manufacturers, they actually tell us what flow rate we get for a particular head, and they do that with pump curves, and that's in the notes. So now the last part of this assignment will ask you to find a pump that will do your desired flow rate. In this case, we've put 10,000 litres an hour. It might be less, it might be more. And will tell you how much head it will overcome at that velocity. So you just find a pump which will do 6.62 metres of head at your desired velocity and put that into your report and just say, I'm going to use this pump because I want to pump at this volume an hour and this which has this amount of head, and this pump will overcome that head with this at this power rating. So that's all pretty simple. So that's for the fixed line. For the flexible line, you just have to calculate instead. If we go back to the map, the plan, what distance of flexible hose would you need to just go along the floor to a pump somewhere here and then over to the bottom of this pump there. So you can just sort of roughly calculate that hose length. Well, the final thing is how many volt amperes, so how much power actually has to be, or how much energy has to be provided by the power station to power our tasks. Well, here it asks you what the power factor is. Here I've put it in percent, but power factor is actually generally in just a decimal between 0 and 1. So a sort of standard pump would be about 0.85. Here it's 85%. So here it says this is actually in kilowatts. I should put that there. The power station actually has to provide about 23 kilowatts to run our 0.195 kilowatt pump. So we actually have to pay for an extra 30 watts per hour to run this pump. So that's all pretty straightforward. This spreadsheet is loaded up on Moodle for you to use. But don't forget to please provide this as a report. You don't have to supply the winery as such, but it would be good just to have lines drawn on the winery to show where your hoses are going. But not 100% necessary. But please do a little mini write-up going, this is the calculations that were done, this was the head that was calculated, and this is the pump that will overcome that at this flow rate. Please also provide your spreadsheet, upload your spreadsheet. So that's a fun little task. And